Cyclotron is a particle accelerator. So we have a particle and we accelerate it. So V1 and now V2. So the particle is being accelerated. And why do we accelerate particles? The charged particles could be electron or proton. There are many uses. One is when we accelerate charged particles, you have a charged particle here, and there's another one here. When we make them to collide, when they are traveling at a very high speed, close to the speed of light, they will scatter into small subatomic particles, and scientists can look at it and see what is there. And that's one of the way that scientists found out that what do we have inside atom other than electron and proton and neutron. And there are lots of medical applications, particularly for cyclotron, that when we accelerate a particle and target to a cancer tumor, so it's a cancer tumor, what would happen is that will kill the tumor. So it's used medically. And there are other uses. We accelerate particles towards an isotope that is a stable one. So we use it on an isotope, a stable one, and we get an unstable isotope. Why? We can use for medical applications to treat patients and through radiation. And there are lots of uses like accelerating particle. They emit electromagnetic waves, X-rays, gamma rays, and all powerful rays that can be used for medical applications, that can be used to look at protein molecules or any other chemicals or mining. So lots of applications using these accelerated particles. If you're doing physics at a high school level, cyclotron is a ideal practical application that has use of circular motion and how charged particles accelerated in an electric field and how they are bent in a magnetic field. And also there's nuclear physics. So it's a combination of lots of basic physics principles that we can see here. So a charged particle getting accelerated in an electric field. And how do we do that? So if you have a metal plate here, and if this is positive, negative, you connect to a voltage source. So you create an electric field between those two plates. And what happens to a charged particle? Say this is a proton, it's a positive charged particle. That will accelerate towards a negative plate. So if this electric field is E and we are applying a source voltage V, and if the charge is Q, then the force on the particle is given by F is equal to EQ. So charged particles in electric fields, they accelerate. So this is what we use in particle accelerators. We create an electric field and make the particles to accelerate from plus to minus or minus to plus, depending on the charge of the particle. And then we have what? Magnetic field. So if you have a magnetic field like that, so this means this is going in, right? So if a positive charge particle enters this magnetic field at velocity v, that particle will move in a circle. Do you know why? Because that v and the magnetic field are perpendicular to each other. So that means the force will be this way and this way, this way. So they will be pointing to a point which is the radius. So it will go through a circle. So that force, because they are all perpendicular to each other, is given by F is equal to BQV. So B is the magnetic field strength, Q is the charge of the particle, and V is the velocity. And now, so as we discussed before, we're using the charged particle in an electric field and charged particle in a magnetic field. Now we're going to use the circular motions equations. So in the circular motion, the centripetal force is provided by a net force. That net force, if we say F, is equal to mv squared over r. R is the radius. So in this case, we are going to get an equation that BQV is equal to mv squared over r. So from this one, we will get an equation for V in terms of the magnetic field and the charge and the radius and the mass of the particle. So these three principles are the ones that we use in cyclotron. So let's look at cyclotron now. So this is a cyclotron. So we have got two magnets, North Pole and South Pole. So that means the magnetic field will be going like that. And then we have got these hollow shapes. It's a bit like you get a cylinder and cut into half, but they are hollow inside. Then we have this oscillating electric source, which will create an electric field between these two plates. But because they are oscillating, they will change from plus to minus. Once this will be plus and that's minus, and then this will be plus, this will be minus. And this is where the source of the charge. So if we have a proton here, and the proton will accelerate towards a negative plate, right? So it will accelerate toward the negative plate. And once it enters here, then the vertical magnetic field here, that's going in inward direction, that will accelerate that proton and it'll go through a circular motion. And then it'll come out, and then by the time it comes out, this will become plus and this will become minus. So these plates, the polarities will keep on changing whenever this particle is going to emerge from this place. So it'll become minus, it'll become plus, and this will become minus. So it goes there. And then you have another circular motion and circular path here, and it will continue. So what's going to happen? That every time it gets accelerated, the velocity increases. But when it enters the magnetic field, the velocity doesn't change. Velocity changing, but the magnitude of the velocity doesn't change, which means because it's accelerating. You know, in a circular motion, the magnitude of the velocity is the same. But when it comes out again, and it's going to accelerate. So the velocity will keep on increasing when it goes through the electric field, but the magnitude of the velocity remains constant when it goes through the circular motion in the magnetic field. So it will continue to accelerate, and when it comes out of this place, that particular charge will have lots of energy, and with that energy, and that be used to whatever the target that we have for. It could be a cancer tumor, or it could be an isotope. So now we're going to look at the how the velocity changes. So the velocity here and the velocity here, and you can compare them, that you can see the velocity is increasing. At the same time, you can also see the radius is increasing. So the radius is increasing and the velocity is increasing. So let's write the circular motion equation for this particle. So if the particle is, say, it's here. So we have a force acting, the centripetal force is acting towards the center. So that centripetal force, Fc, that centripetal force is equal to mp squared over r. That centripetal force is provided by this magnetic force, which we can put as BQV is equal to mv square over r. So here the v and this 2 will cancel out. So we can say v is equal to BQR divided by m. But we know that v is equal to 2 pi r over t, right? So we can say 2 pi r over t is equal to BQR over m. And now we have r, and r will cancel each other. So we can say that t is equal to 2 pi m divided by BQ. But t is 1 over f, that is 1 over frequency. That means the frequency is equal to BQ over 2 pi m. So this is the most important equation in cyclotron. Why? The frequency of this oscillator that provides the electric field. So this is the electric field that's providing the electric field, and the frequency should be equal to the frequency of these circles. So that f is equal to BQ over 2 pi m. So let's write it here. So f is equal to BQ over 2 pi m. So what does this depend on? So it doesn't depend on radius or anything. It does depend on the magnetic field, the charge, and the mass of the particle. So BQ over 2 pi m. So this is quite an interesting one, because for a cyclotron to function properly, this frequency should be equal to the frequency of these circles, and this is a constant because B is constant, Q is constant, and the mass is constant. And we're using a standard electric source, an alternating source. If we consider the relativistic effect on these accelerating particles in terms of mass, because we know that if the speed is close to the speed of light, the mass increases. So what happens when the mass increases? If the mass increases, that's going to affect the frequency, right? So that means that we should be able to adjust something else here to make sure that frequency matches this one, right? So cyclotron hasn't got that ability. So we will be looking into a synchrotron, another particle accelerator, where we will be able to adjust the magnetic field to keep the frequency constant. So to summarize what we have discussed, that the velocity of the particle at a particular stage is given by this equation, which depends on the radius. So the radius changes and the velocity changes. But when we look at the period, it's the same. So the time it takes for this particle to go from here to come here is same as it takes from here to here. So that means the t is the same and the angular velocity is the same, but obviously the velocity is different between these all three orbits. And we have got an equation for frequency. So let's write this frequency as f, the circle, and this frequency as fe. So fe should be fc for us to have a successful operation with cyclotron.